Would you like to use? Use something general first to make these work.
Good. Okay. Hello. I'm going to be talking with you guys about this plane. So the plane is first define displays and give some basic properties. And then we'll switch to like a linear algebra viewpoint on displays, which allows us to describe the stack of displays and the stack of truncated displays. And then I will sketch how you associate the display with over a range. So yeah, some things will have more details on it. So the first thing is generalization, which comes from Dieudonné theory. So I'll just recall a few things that we've heard before in the sum of the theory. So let K be a perfect field of characteristic B. So recall that classical Dieudonné theory gives us a classification of p-divisible or Barsotti-Tate groups over K in terms of Dieudonné modules. So is this big enough here? Or
Yeah, we answered. So.
It says that there's an equivalence or anti-equivalence categories between okay, I'll be putting that to Dieudonné moduli. So finitely the K modules equipped with sort of Frobenius linear and Frobenius inverse linear maps that multiply. So I'm equipped with sigma linear. And such that really that's what the classical theory says. And if we're trying to generalize this to a general ring or an equivalent or a characteristic P, then you immediately run into the issue that sigma inverse no longer makes sense on R. So the general R sigma is not equal to and yeah, so sigma refers to the bit vector Frobenius. I will write the sigma later, but after the manipulation, essentially. So we might try and fix this by defining Dieudonné modules over a general ring, where we replace this V by the map to the Frobenius twist. So if I replace this by a Dieudonné module, R is a finitely generated projective. It's a finitely generated projective WR module. Equipped with linear maps. So we'll use a sharp to denote like the linear version of software. So So the F is the same as the giga of the F above, because sigma linear maps correspond to just linear maps of the Frobenius just of the module. But the V is only equivalent to a V as above when you can invert sigma. So this is kind of a natural way in which you might try and generalize the definition of a Dieudonné module to an arbitrary ring. But there's still some issues with this definition. So I guess one sort of issue is when R is not perfect.
But R is now still a K algebra or?
Oh yeah, sorry. I should say like maybe I can say R is a P niltoton ring.
Ah.
Yeah, so our goal will be to try and sort of devise some suitable analog of Dieudonné theory where you replace the base with any sort of P niltoton.
So then perfect means what?
Perfect means characteristic P and perfect. Yeah. When R is not perfect, yeah. Right. Yeah. So I'll give the definition of that like more precisely. But it's just a way of turning a sort of sigma linear map into a linear a different module. So when R is not perfect, WR can have P torsion. And we could lose some information, for instance, if F is divisible by P. So, and so, like one way to understand what this means is that if f of x is divisible by p, there can be multiple ways in which it is divisible by p, and sort of so the situation is somehow not rigid, and you want to keep track of the object which sort of witnesses why f of x is divisible by p, and so that's like the modification that you make to get to its square, to get to its square. So the observation that you could make is that on submodule. Oh, I guess we should. That might be perfect with diversity. And so the observation that one can make in this setting is that on the submodule, of V of M, we have that PV inverse equals M. And so this V inverse somehow is recording why F is divisible by P on that level. So P inverse witnesses the divisibility of F by P. And the idea of displays is to keep track of these as extra data. So that is what we'll end up doing when we define displays. I should say that this kind of makes sense because V is going to be injected when you're in the setting of a perfect field of characteristic P because F times V equals P. So, are there any questions about this motivation?
Yeah, that one.
So now we'll define displays. So let R be a p-nilpotent. And let WR be the vectors of R. And because I'll be using a lot of F's and B's later, I will say with Frobenius sigma. Sigma and the Shiva lowercase e. And we will let I sub R be the ideal, which is the image of B. So the image of B, which is the same as the kernel of the projection map to the first factor. And if we have a so M is a WR module, we'll write M1 to be its twist by the Frobenius subgroup. So this means that we view M1 as a WR module where the action is given by multiplication on this factor. And if you want to move a scalar from here to there, then it has to come over with a factor of sigma. And the point of doing that is that B from M to M with a single linear map of modules, then we can just linearize this. D sharp. And in this case, we would define G sharp by G sharp as the M. That's the. So that's just like a bit about how you linearize a map, which is for these. So then the definition of a display is as follows. So a display over R is a quadruple of P, Q, F, F1, where so P and Q are going to be WR modules, and F is going to be like a Frobenius, and F1 is going to be like this inverse to Barsotti-Tate from up there. So the formal way to say what these are, what the properties are, would be just to say where P is a finitely generated projected WR module. Q is a submodule. And F goes from P to P. F1 goes from Q to P. Or Sigma linear now. They have to satisfy some extra conditions, which basically are modeled on what happens for a Dieudonné. So such that so Q has to contain this ideal, the submodule of P generated by this ideal. And P over Q is a direct submodule. So P over P. The second is that P is generated by the image of F1. And the final condition is that F1 is some relation that is exactly satisfied by V inverse of F1. So we're kind of secretly thinking. So thinking Q given that so that's kind of the keeping track of the V inverse of M, and the V inverse structure is exactly what we're doing with this definition. Are there any questions about the definition? Okay, so I should say that just say what morphisms are, and so we get an actual category of this place. So a morphism yep. I think X lying
What's the question?
oh, he was asking if is X lying in P or X lying in Q. And I think it's X lying in P, because then this term will lie in Q. And
X Y will apply to you.
sorry.
What then essentially did not double 4 5, but it's a
yeah. Then here what yeah.
Okay, yes, absolutely. Thank you.
So morphism of this place it's just kind of what you think it should be. It's a map from P to P prime that takes Q to Q prime and commutes with applying F prime at one prime. So it's all that. Prime. And compatible. Right here. Oh yeah. Okay. And so this leads to a category of displays over R. And since these are going to be related to p-divisible groups, we can also speak of height and dimension on a display. So height. Just the rank of P. And the dimension is the R rank of P1 Q. And so the height is like still a locally constant function on P, and same with the dimension on it's a locally constant function on spec R. So it's like in analogy with how you might expect the height of Barsotti-Tate groups to work. And
so can I ask?
yeah.
So in general, you're not going to be able to extract this Rashomon from this data, or
you will be able to.
you will be.
In the case of yes, so there, yeah, you will be able to extract.
You,
I will explain the equivalence with Dieudonné models in the perfect case.
but in the perfect case,
In a non-perfect case, there still is a canonical way to get. Yeah, so there's always a functor from displays to Dieudonné modules, which I'll explain, and then I'll explain the inverse functors when there's a perfect. And so I also just want to say that there is a natural notion of base change of displays with respect to ring morphism. So, but I'm not going to write it out because it's a little bit cumbersome. So, base change. With respect to morphism of rings. And the point of this is just that displays will naturally give you a category fiber-name groupoids over penal codices. So eight. Give the category.
I just remembered something that is the dimension on the display. Um, is the dimension of it is like when you do the Dieudonné in the perfect case Dieudonné to display, is the dimension just not extra dimension?
Sorry, please say it again.
I think he said yes. Thanks.
Is it? Is it some sort of
I don't think so. I think it's what? I think it's additive. I'm not sure. If it's exact.
what do you mean by that's?
Well, like projected models.
Oh, I see.
I think that it's nice.
So you ask whether it's a BD.
Yes, no, I don't. That's not a medium, but it may have nice short sense as well as.
Okay, so a few remarks on this definition. If we take sort of the speed equals 1, as Sasha was saying, and the definition of displays, we get the relation up there reads f of x is equal to f1 of so f is uniquely determined by f. And the second thing is that if we take x in Q, the above, then we find that using that sigma v equals p on the bit vectors, we find that f of x equals p f of x for all x. And so this kind of makes a bit more precise the sense in which f1 is keeping track of when f of x is divisible by p. So if you think about f1 is a perfectly defined divided. Right, so now we'll discuss the relation between Dieudonné modules. So as we said, one of the main motivations was to generalize Dieudonné theory, and Dieudonné theory works perfectly well when your base is perfect of characteristic B. So these had better agree with Dieudonné modules when the base is perfect of characteristic B. So now explain why that's true. If R is perfect with characteristic B, that displays the category of displays over R is equivalent to the category of and so first we should note that when R is perfect of characteristic B, the bit vectors of R have some special properties. So since R is perfect, the Frobenius on the bit vectors is an automorphism because it's just induced functorially from the Frobenius on R. So since furthermore, the Frobenius times the Hershey-Bone is P, or the composition of this P, we can deduce that WR is P torsion free as well. This ideal that we described earlier is just the ideal general equation. And so these are the key properties which will allow us to go backwards from, yeah.
When you say R is perfect, you mean like a ring with Frobenius isomorphism, not necessarily a view?
Right, yes, yeah. Yeah, so it has to be careful. So let's start with the dude. So let's start with the Dieudonné module over R. Then the motivation kind of gave us the recipe for doing this. So note that E is injected. And we get it. Kind of the recipe we gave for going from Dieudonné modules to displays. And the other direction is to start with the display and produce a Dieudonné module. So I guess there's something like why, right? Obviously. Display. We already have the module and the Frobenius, so it really just remains to define the Verschiebung. So we define this nonlinear map. The linearizing I'm sorry, this is linear. So we're going to describe the map whose linearization, which is the same. And so we know that places to define the sharp one image of F1. Because one of the hypotheses in displays is that the image of F1 generates the whole module. And so now we're in good shape because we've kind of gotten rid of the P. And so we just set V sharp of X to be one answer. So I guess I should write it up. And again, there's some things to check here, but like namely that FB equals VF equals P.
More worried about whether this is well defined.
Yeah, so
more generally.
yeah. So it is well defined, and one of the ways to see that is using, so it will use something that I will discuss later, and then I can tell you why it's well defined, if that's okay.
Okay. Yeah.
But I should say that the fact that FB and VF equals P is essentially a consequence of the two relations that like F equals PF1 and that sigma of B equals P. So it uses something very general which doesn't really use the perfectness. So remark. So the second direction there didn't really use the perfectness assumption. So
Do you use the requirement like the assumption that R is characteristic P? Do you use VF equals to P?
For
Is
this,
this
no,
you also
yeah. For the first one, yes.
Yeah, right.
Yeah. So,
But that if you use the perfect thinking for FX, and then people equals. Yeah.
sorry.
And the perfect situation, they image of what you want equals
Equals the P.
yes, equals P.
It's the inverse.
Yeah, I guess yeah.
But this it's enough if you are on thinking check in case of not perfect
Yeah.
things, it's not clear, it's enough to find that it's not generic something. Well, could be something.
Like you mean because of well-definedness?
Yes.
Yes, yeah, right. I agree. So the well-definedness is, I think, the key point, and I guess I'll hopefully remark about how that happens.
So the principle you use.
Yeah, I guess in principle, yes, but in reality, no. But yeah, thank you. So. So yeah, is there a mark? So I guess as the point that I'm hiding shows there's a functor from displays to Dieudonné modules, even in the setting of non-curve. So the proof shows that we always get displays over our to Dieudonné module.
But again, it's
Yeah, yeah. You mean like, do you mean this, the fact that this extension makes?
Yeah.
Yeah, there is something.
More than that, right?
you prove that it's really fine. That's
That it exists. This remains that it exists, yeah. Sorry?
Yeah, so there are two complications. One of them is that F is not an isomorphism. The second is that VF is not P. Okay.
Yeah. But in this, I guess so far we've only used that FB is P. And that PF1 equals F on this submetric.
Well, you mean for the well-definedness?
Oh no, for the well-definedness, no, but for the proposal
Yeah,
for
sure.
P1.
Yes.
Yeah. So over a P multiplication. But I guess when there's P torsion in the bit vectors, then this functor does not need to be fully fake. I guess the point I'm trying to make here is just that this tells you conceivably how you get more information by passing from displays to Dieudonné modules, because there can be multiple F1s which give you the same P times F1 in the presence of P torsion in the vector. Are there any other questions? Okay, so now I'll remark about the tool that ends up being used to prove the existence of the function. So it's called normal decompositions. So a normal decomposition of a display is a direct sum of the decomposition of the P. Plus L into two submodules, such that Q is equal to T equals. So it's some tool which allows us to further simplify the situation and study sort of these two submodules, T and L, instead of the whole P itself, because Q is just determined as well. And sort of the fact is that normal decompositions always exist. Well, questions? And the reason for this is because basically you can lift finitely generated projected modules. If your modulo like an ideal for which your ring is complete. since P mod Q is a direct summand. There is a finitely generated. Projective moment. And since WR is IR adequately complete, you can lift this P mod Q to a projective WR mod. There exists a finitely generated projective W module E and a projection. I think this is some general fact about projective modules over like modding by I gives you an equivalence of projective modules of a ring and R.
And this is because you can leave them both.
Okay. And so let L be the kernel. So we'll just take let L be the kernel. And then so that P equals L plus P. There exists a splitting. And Q is just the kernel of P. The P mod Q which is just the kernel of P plus Q. L plus so should I keep that definition up or? And so the following is the key lemma, which lets us describe displays in terms of matrix. So lemma. So if you have a display and a normal decomposition, then you can kind of get away with less data to describe the whole display. So display P is determined by its normal decomposition together with the restrictions of F and F1. By normal decomposition. F restricted to T, and F1 restricted to L. And moreover, if you take their direct sum, is a sigma linear symmetrical. I guess the claim of the lemma is that you can kind of recover F on L and F1 on T from these two pieces of data. So So we have F restricted to L is just P F1 restricted to L. Also, F1 restricted to L. Right, so I guess so we get at the point. And similarly, C times F of T equals F1 from here to C. C well, so we get F1. Sorry? Yeah, I'm just saying if you have an element like this and you apply F1, this is like a general element of IRT. Then it's just recoverable from F of T. And so, and the linearization, well, with the map. So I guess I'll say that if the phi surface show that the linearization is surjective because it's a map of projective multiples of the same thing. So suffices. Oh. Projective. And this just follows that from the fact that P is generated by the image of F. So I'm kind of putting some details here. But yeah, I'm skipping a few details here. So if someone wants me to solve them on the argument. So the thing we want to do now is use this lemma to describe displays more explicitly in terms of matrices, because it tells us that giving a display is kind of like giving this signal linear isomorphism T plus L to P. So third section. I guess we also need a break, right? When now
It's 5:24 right now, so.
like before I start this section, it might be time for a break. Okay, so yeah, now we're going to describe displays in terms of matrices, which will lead to an explicit description of the quotient stack of displays. So, and I guess this is an approach explained in this paper by Wellfell and Papas. But probably these ideas were, I think these ideas were sort of known earlier, at least. So some notation that we use is so that GLH W be the functor or goes to GLH W and R from P of different rates. and it's represented by an affine group scheme over CP. Essentially because the multiplication and addition on the bit vectors are determined by sort of universal polynomials, and so you can just think of like adding variables for each of the coordinates of the bit vector. And the second thing is the same thing for truncated bit vectors. So GLH of WN is the pointer R yeah, and it is representable by an affine group scheme over FP. And moreover, the truncation, since GLH is smooth, the truncation morphisms from GLH of the truncation morphisms from GLH of WN to GLH of WN minus 1 will be smooth. So truncation.
And why do the want the option myself, I guess, eat and what is the culture?
Yeah, so I guess when we define displays, we'll work with all p nilpotent rings. And when we define truncated displays, we'll be over FP because we want the Frobenius to be an endomorphism of WN. So you don't want to have to take truncations like to define Frobenius.
But that's for future.
Oh, I see. I guess
at the moment you could pay.
Here, I think I could.
Yeah.
Yeah. Yeah, I think that's correct. I guess I was just taking that because that's all we'll use, but yeah. GLH is WN is smooth. And I think the smoothness can somehow be deduced from the truncation morphisms being smooth, but I'm not entirely clear on the details. But these are sort of affine group schemes which we'll be using. Because we'll be talking about matrices with coefficients in the vectors. Okay, so now we'll talk about displays.
Am I right that you can consider just the domain accessible by UTL or something like this? And actually each a matrix is invertible one way even not if it's projection.
Oh, okay. Oh, then you get them. Yeah.
One of you two repeat questions.
So I'm just saying, what does it mean? What is GAH? This is an invertible. When is a matrix over couple of is invertible? Even only if it's projection to the corresponding matrix when you double zero and R itself is invertible. And so so the projection for GH that can be GH double and then second one, but 5% just all matrices. So it's smooth for the reasons of double event or double projection. The 5% is the same.
So now we're gonna use this to describe displays using the normal decomposition. So again, R is no perfect. And P is a display. And we have and fix a normal decomposition. So, normal decomposition. So the risky locally on R, all of these guys are free. And so we'll be able to describe sort of T plus L and the map F plus F1 just in terms of a matrix. So R. T and L are free of minus E and H minus D respectively. And so basically when we want to describe the quotient stack, we'll just choose bases to rigidify the situation and then quotient down by all the automorphisms, and that will be the description of the quotient stack. So if we choose bases, P is determined by the block matrix where sort of A has size D by D, and D has size H minus D by H minus D. So A is kind of the map from T to T, B is from L to T, C is from T to L, and then D is from L to L. And we just have to like unwind what a morphism of displays looks like in this language, and then which morphisms are isomorphisms. So I'm not, I'll just explain what ends up happening. So a morphism of P to P prime is given by some matrix H in GL H of WR, or sorry, not GL. Just n minus C. Sorry,
Should that C be a big 0?
that's C be the big 0. No, I guess it's just a C.
Just C.
Was it like a notation question or just?
I didn't know this notation was. Was that from the question about C?
Yes, I think C can be the. And it's an isomorphism in H and GL HMR. And then we just need to understand what restrictions are placed on this matrix by the fact that it has to take Q to Q and be compatible with F and P. So we just need to so I'll say H sends Q to Q sends Q to Q prime implies the H can be written in the form, like we're gonna write it as a block matrix X, V of Y, Z, T. And where this V of Y means apply V entry wise. Y, V, entry to Y. So in terms of the normal decomposition, that's kind of clear because Q is L plus I times T, and so in order that you land inside of I times T, like the cross map that would be divisible by V. And the compatibility,
T is different from.
oh yeah, T is not related to the, yeah.
So
Yeah.
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 That's so
Yeah.
in the situation, like if you're over a perfect field of characteristic P, then isn't it C0?
So C is the map from L to L.
No, at T to L, right?
Oh, sorry, yeah, C is the map from T to L. Yeah.
Which is like this V map.
I'm not sure. Is it? Do you have a reason or?
Seems, I mean, seems to me like this T, at least intuitively, T is like where V is divisible by P, and L is where V is divisible by P. And if I have something in T and I map it by V, then I shouldn't land in a place where Frobenius is still divisible by P.
But if P is not 0, then couldn't that just be? Oh, you say if K was a particular thing.
Yeah.
Oh, yeah. Then that possibly, yeah.
I don't know.
Yeah, I'm not sure.
Sorry?
Okay, so compatibility with F1, F1 prime. If you work out what this means, it ends up just being a matrix equation. It is so if this is the corresponding data for P prime, then you multiply it by. Yeah, you're right. I think you're right. Yeah. You probably have to clear it. So this ends up being the conditions. This ends up resulting from the conditions that it's compatible with F and P. So these sigmas are showing up because F and F1 are both sigma linear, and then this P is showing up because on L, F1 is P times F1. F1 times P is a. So using this, and then finally we can say that H is an isomorphism. If it is going to be allowed, if it is going to be. So using this, we have enough to describe the quotient stack of this split. So let H E H minus E will be the subgroup of GLH or GLH of only consisting of matrices of this form. And set P of H to be this matrix here. And Y, And so then the above analysis shows that displays of height h and dimension d are the quotient of GLH by this p conjugation action of this subgroup of HD h minus d. Because here, if the matrix was invertible, you can just turn this into a conjugation. So we can write that. The result is this proposition that this infinity h p isomorphic in the quotient where the action is given by phi conjugation.
Right, what is H? HD.
Oh yeah, so it's the subgroup of matrices consisting of things where this block is via base.
Is that clearly like a sub?
Okay, so
I think you can just question out the ideal. It's the lower trappings.
Okay.
sorry. So where the action is just given by hx equals h inverse x. So this gives us an explicit sort of quotient stack description of displaying the height h and dimension. Any questions?
Sorry, yeah, I'm still a little bit confused. Sorry. So I thought when you write down this matrix, you sort of fix a normal decomposition, but I'm maybe
Yeah, I guess we are like choosing a normal decomposition and like local bases. So we're saying like every display Taritsky locally on the spec R is like a torso for this group H D H minus D, which looks like GLH locally. So it's like saying that basically it's given by this kind of data. Any other questions? Sorry.
So you say that R is the base feeding.
Yeah.
He needn't be in
Or wait, for B on the
lowercase b.
yeah, I don't
Wouldn't be so.
yeah.
So therefore, the same matrix in H can be represented in different ways, right? But you can change Y.
Oh no, I think B is injected.
Ah.
Yeah, I think because you're considering the whole bit vector, so it's just shifting. So it should just be yeah. Yeah, that's the key point when we talk about truncated displays is that the V is no longer injective. So instead of because the Y is uniquely determined from like the other Y, but later we'll have to take us two matrices because of so yeah. Yeah.
sorry, why is this a covering?
Y is what?
Why is this GL H of W a covering of this module? Namely, why does every invertible matrix realizable as F composed with F1? Or is that
Like you're saying, why do we get every matrix? As,
yeah. Sorry. The lemma.
But is your question like why is every element of GLH? I think the choice of an isomorphism like that like also lets you recover
I
its
see.
display structure. Like
So if you, I see, so the claim is that if you have an isomorphism from P to P basically, which is theta, which is signal linear.
Yeah.
Then you can find
yeah, if it's given by this like direct sum decomposition P F plus F1, then yeah, you can find display that.
Can I say more that wood is something about if you think of P as first come over to
Yeah.
U is actually the first one on which the
Right.
yeah, the data of well, the data of composition is that we need this watch equation which is defined by R. Yeah, so something and also the transverse.
Sorry, no one.
And also the peak and transverse.
Yeah.
Yeah, and this is the relation which is
By transverse you mean just a splitting. Yes, yeah. Yeah. Okay, so now we'll talk about the case of truncated display, which should correspond to truncated Barsotti-Tate groups. Or not correspond, but yeah, will be associated to truncated Barsotti-Tate groups. And so I can say that the notion of truncated display has a definition in terms of like 2 WN modules with some extra data. And it's defined in one of these papers of Lau, which I'll give reference to at the end. But I think that that definition is pretty complicated, and the advantage of this matrix approach is that it's essentially we can define truncated displays to be this quotient stack where we replace W by WN. So that'll be right here. So I'll say that in Lau, this in the 2013 paper of Lau, which Renfeld has been discussing, we can find the definition of truncated display in terms of sort of vector bundling type data. Complicated. Right. And the advantage of this approach is that we'll just replace the matrices and replace W with W. And as was pointed out, we'll have to be a bit more careful this time because of the fact that D is no longer in check. Yeah.
You say that you have but if you go in the same manner, you seemingly recover only for poets. You know what you the back is over different cases. Or you can understand in this simpler way also both parts.
Oh, I guess the way I'll formulate it is to describe the stacking group points. So I guess we would only recover isomorphisms, but I would assume that there's a way in terms of matrices to also describe this one. Like probably if you replace the GLH of WN with H of WN and subject to Then what can you get? I'm not telling you. So I guess as was pointed out, there's an important distinction here, is that sort of warning. E from WR is injective, but E from W N of R need not be. So in context of displays, we can't recover Y from B of Y. So recover Y from B of Y. The way around this is just to keep track of the Y as well, and keep track of two matrices instead of just one. So we define a subgroup denoted BPNHD. So the BP, I think, is notation from Drinfeld, and it stands for Miltel Tapas. Inside the product, and it's going to be pairs of block matrices. So you see what I'm doing here is just keeping track of the H and the P of H both, and then the action on GLH will just be conjugated. So P conjugation is just sort of P H of X equals H inverse X P. And we'll just define the truncated stack truncated displays of level n to be decompositions. Slash proposition depending on stack.
Okay, just a notational question.
Yeah.
What do you mean by V of Y?
I mean, sorry, apply entry wise to the elements of Y.
Y is in
X and all of these are in W event. And so these notations just mean apply Frobenius and Verschiebung entry wise. Oh, sorry, I should also say weird characteristic. No. That are but that's the point of confusion. Okay, thank you. So stack is and HT of truncated display H in dimension 3 is the quotient so it's a stack over, it's an algebraic stack over F, and it's defined to be this quotient. Sorry?
P with this.
Yes, subgroup of of this product. Sorry?
Slash I. I mean, it's a portion.
That's a quotient modulo this.
Modulus is
yeah. And it's acting on the field HP as its kind of conjugation. And so one advantage of this approach is that we can immediately see a few things about this stack, like smoothness, because it's a quotient of something smooth by a smooth group, and dimension 0 because this data is just the data of like a matrix, and so these two have the same dimension.
Is BPN obviously smooth?
Sorry?
Is BPN obviously smooth?
Yeah, I guess so, because all of the equations which define it are in the form of variable equals p power of variable and so on. So after some cancellation, I think it will just be like there's no like p powers that are gonna like mess up the smoothness. Yep.
Also, like just a trivial affine bundle over GLH.
Sorry.
It's also just a trivial affine bundle over GLH.
What do you mean by that?
Never mind.
I guess it has a map from GLH, I guess.
Hmm.
Like it has a cover of it is
Okay.
GLH and well, I guess let me write it down. So the corollary this n, or I mean you could put HT as well, but or just this n is a smooth algebraic stack over FP of dimension 0. And the natural truncation morphisms are smooth and surjective. So the analog of sort of the growth in the smoothness theorem in the setting of displays is much more straightforward than Bertrand's theorem. So are there any questions before we do some examples? Okay, so now as an example, I want to spell out in detail what you get in this definition when n equals 1, as that gives some indication of the relation with Barsotti-Tate groups. So example. And this is explained in a paper of Drenfeld. It's his first of his 3 e-prints from this year. So we're going to find that basically points of BT1 over FP schemes look like the structures on the Ron cohomology of smooth proper schemes in characteristic P. And this one will be what happens when you kind of forget the Gauss-Monnian connection on that structure. So when n equals 1, in this definition, sorry. When n equals 1 in this definition, we're working with no bit vector. So P is 0 and B is P is 0 and B is 0. So this simplifies considerably. So zero and zero. And we'll consider the following block clusters. So we consider M will be the block diagonal matrices. P plus will be the parabolic of block upper triangular matrices. And P minus is the block lower triangular matrices. And under this, the BP subgroup, BP1, HP is just those pairs G and H, P plus times P minus, such that their diagonals, like one of their diagonals is the Frobenius of the other. So DM equals so if you look over here, the H is going to be lower triangular and the G will be upper triangular, and on the diagonal, if you apply sigma to H's diagonal, you just get G's diagonal. And we have a short exact sequence which characterizes BPs by this condition. So where this is kind of right, because BP is exactly those matrices and P plus times P minus, whose kernel is. And now we're just going to apply a few general facts about classifying spaces to study the quotient stack. So let me just write the facts of this. So to analyze this one equals H1. We use the following facts. So the first fact is that if you have a morphism of group schemes over a scheme F, then there's an induced map of classifying spaces, and you can say what the universal what Forster induces that. So the map group schemes then H mod B is an H Forster PG sort of a Cartesian square. And the second fact is that if you have an exact sequence of group schemes, then you can say that K torsters are those G torsters which become trivial, whose associated Q torster is trivial. So a way to write that classifying space of K is just the classifying space of DG times the trivial map over B. So t-value points, like to give a K tensor is the same as to give a G tensor together with an isomorphism of it with the trivial T tensor. And so we're going to apply that to this exact sequence so that we can say exactly what's going on. So we find that this one HP is just a fiber product of the classifying space of BP1 times and moreover we can say what this classifying space is because it's a subgroup of the product, the exact sequence. So for this one, I'm using the first fact over there, and for that one, I'm using the second. So using these two facts and the fact that the action of BP on GLH is by conjugation, we see that like to say that the associated, for instance, P plus times P minus tensor on M is trivial is just the same as giving an isomorphism of the P plus tensor of the M tensor corresponding to the P plus and the P minus. So
M is just a product of two products, right?
sorry,
M is just what is M?
M is this locked diagonal matrix.
Oh, so it's just two products.
Yeah. So this leads to this a one truncated display at H dimension D over an FP spin S consists of the following data. Sort of first is the pair of tensors for P plus and P minus. So P plus minus plus the second is an isomorphism X plus M with the Frobenius pullback of X minus M. So this is eventually due to the fact that we define the map here is like kind of conjugate and take Frobenius. And then the final thing is an isomorphism between the corresponding GLH. So this is kind of what unwinding the quotient stack description tells you is the data of a one truncated display. So we can say
Sorry, and this moduli space maps to the moduli of BT1, right?
BT1 will map to it.
Oh,
Like to a one truncated Barsotti-Tate group, we will be able to associate this point. And you can see exactly what that maps.
so but in the infinite level,
Yeah.
you have a map to
And there is some other maps from displays displays to infinity. So there's a map from displays to infinity smooth groups and truncated displays to n smooth groups. But I guess we are more interested in the maps in how to get a display from them. But that map is an equivalence. The infinity one, like sort of between so-called nil quotient displays and infinity smooth groups, it's like an equivalence. Okay, so we can look at
There's something like this, but you have, you have a space, and you have there two, two step integration, two subspace. One is called second integration, another conjugate integration, and the option.
Why?
Yeah, and then when we talk about PT1s, then they'll efficiently be a flat connection such that it satisfies some equation.
I mean, I kind of see where the Hodge prediction comes from. Where's
Yeah, so I'm gonna explain that. So more concretely, we could so the PLH or the S is no is the same as a vector bundle. When we look at these P plus and P minus sources, then so P plus P plus is the subgroup of GLH which stabilizes the d-dimensional subspace. And so the transition maps of a bundle being plus exactly means that you're singling out a d-dimensional subbundle of your bundle. So this is like here.
It's not only the people are talking about the multiplication of the corresponding GH.
But the P plus sourcer is the vector bundle with the subbundle?
Yeah.
Right.
Yeah, just the same thing. But okay, I'm sorry. Yeah.
You
Yes.
mean,
Oh, yes, yes,
you
yes,
mean
yes,
it.
yes.
Okay. But it is true that this pairs.
Yeah.
Where E prime. And so and P minus cursor, P minus would be like right, H minus P. And so what you end up seeing is that the data of the P plus cursor together with an isomorphism of their GLH cursors is the same as giving a single vector bundle together with two subbundles.
well, one of them is technically speaking, one of them is subs, the other one's a quotient.
Oh, you mean this one is a quotient? Right? Yeah, wait, so the P minus is a quotient?
If that's what you're writing, maybe I'm misunderstanding that.
Yeah, I think you're correct. Yeah. Yeah, I think you're correct. Yeah. So I guess I'll write what I was originally going to write, but so the 1 and 3 is the data of P together with sort of two short filtrations. And so in our heads, we are thinking that the structure is like that of the Dieudonné homology of a smooth proper S cube. So and so what ends up happening is that BT1 has a description which consists of these three pieces of data together with a connection, which is supposed to be the Gauss-Bonnet connection. Oh yeah, sorry, yeah. So yeah, when you add two, you also get yeah. And so there's the following theorem, the theorem, and it was originally conjectured, I think, by Drinfeld in this preprint, and then Lau explained to him how it follows from known results in crystalline Dieudonné theory. So I guess I'll write conjecture Drinfeld. I'll say proved by Lau, but it's unpublished. So, is that an object of BT1? So BT1 S consists of 1, 2, 3 together with a flat connection on that vector bundle satisfying certain extra conditions. Satisfying. And in this situation, the map from BT1 to disk 1 is just forgetting the connection. So, are there any questions about this this description? So I don't know what the proof is. But I guess I guess I should write think homology with Casimir. Okay, so the final thing which I'll discuss is how to go from is the rough idea behind going from Barsotti-Tate groups to displays. So I'll explain sort of how this group works in a special case when you assume that your p-divisible group is the p-divisible group of an abelian scheme. To avoid having to use specific things about crystalline Dieudonné theory. So there's two sort of steps to this. So I should say that this is explained in so first, crystalline Dieudonné theory. Go from a p-divisible group to something called a filtered FP module, which is just a Dieudonné module with a distinguished submodule. So these are hard goes to get filtered. And the second step, which I won't really discuss, is to show that always in this situation that this filtered FB module is canonically recovered from a display form. Upgrade to display over R. And since I won't talk about this, I'll just mention sort of some of the ingredients that go into that, which it uses the Grothendieck theorem about smoothness of the truncation functors from DTN. So and essentially what you need to do is go from a filtered FD module to a display in sort of a universal case. And what Grothendieck's smoothness theorem lets you do is argue that the universal case will have no p-torsion because you can kind of present the stacked dt by some reduced scheme. So is I don't know p-torsion. And it's not so hard to go from filtered FP modules to displays canonically in the presence of without p-torsion because you can just divide. So let me just briefly say some things about step one. So let us first define a filtered FP module. And I'll just say it's a Dieudonné module with a short filtration. So the Dieudonné module. So it's just a weakening of the notion of display where this Q doesn't interact with F or V at all. And so Q doesn't. So that's the definition. It's just kind of a natural target category. So let's assume now that T over R, our p-divisible group, is the p-divisible group of an abelian scheme. Then the idea is that we can just use crystalline cohomology to come up with our P, and then as Sasha mentioned earlier, Q will come by lifting the Hodge filtration on Dieudonne cohomology. So let P be the first crystalline cohomology of H. And P mod IP is just the de Rham cohomology of P mod IP is the de Rham cohomology of A over R. So that'll be the first step of the Hopkins thing. There's only one step, so it's step. So so because I mean we're just in a situation where we started with this WR module, and to give a submodule of that containing IR is just to give a submodule of P mod IR, and that's our Q. So Q be the containing P and this is Q. And this is Q. Yeah.
Are we assuming R is characteristically unique?
No, I don't think so.
It's a crystalline cohomology makes sense.
Right. So I guess, yeah, I mean, like, you can still kind of define the category of all PD thickenings of A, or where, like, you use the small crystalline site to kind of take open immersions.
Okay, sure.
And then you can kind of take the structure sheet of A and like push it forward to R and then evaluate it on the PD thickening corresponding to WR, and like you'll get a WR.
I think my concern was whether the WR was a PD thickening, but
Oh.
I think I should just.
I think WR will always be a PD. Like IR will always have a canonical PD structure, I believe. And yeah, I believe that's true.
Thank you.
And the only thing that remains to be done is to define the F and the V. And for this, we observed that we can work over R mod P. So H1 first of A over WR. Well, I guess I should say since divided powers on IR are compatible with P. This crystalline cohomology group is isomorphic to the crystalline cohomology group, where we consider the special fiber of A and use the same thickening.
And isn't just isomorphism, not isomorphism, isometry.
Sorry?
I'm just repeating the wording that suppose that you have a variety a variety over interconnected zero, but over some maybe high identified expansion of does it mean that you want to intensify the outcome which is the I'm just a little bit worried that it's a situation there will be identification up to I saw general.
Like up to isogeny of these.
No, don't you assure that if you have any that you have suppose that you have a variety over FP, a given variety over FP, then some of its characteristics, not over CP, but say over some highly ramified thing. Look at what you write. You would not even imply, maybe not, that crystalline carbon your initial variety over FP is the same as the round which over the sleeving. Yes, because
Well, it's,
in the sense that you are being
yeah, I guess, but here we're taking W R, right?
yeah.
So in that situation, R would already be CP, right? So, or R would already be some ramified extension of CP.
Yes. But would not be but it projects onto R. It's would not it's the ramp up of the chain just over this high thing be just restriction of the crystal
Will there be divided powers on the kernel of that projection?
from W from R to R.
Or the from highly ramified extension to CP?
No, maybe I'm just sorry.
Yeah, I'm not sure. It doesn't seem to me like it's implying that, but I'm also not super familiar with that.
So
No, so I think that the point of doing this is because we want to define FNV, and so we want to induce them from the FNV on the ability guarantee, not P. So it's like very interesting. And so I guess this is the idea for how you get a filtered FV module from the p-divisible group. Let's finish by just saying like a sentence about how the truncated version works, but I'm not entirely sure how the whole truncated version works, so I'll just give a flavor. I mean, to define the end. Kind of the idea is that if our ETN can be written as the kernel of a morphism of p-divisible groups, then use those to define the truncated. Right? If our VTN and the idea will be to take the displays associated to G and H truncate and then take the co-kernel of the resulting morphism to define our and split is something like and I mean, I think a lot more work is needed to make this definition work in general, but again, the growth in this theorem comes up because it implies that this can always be done after a sequence of faithfully flat ring extensions. But such that it is true for the so you have to make some sort of base change by this limit, this direct limit of these flat ring extensions, and then do some sort of descent to define the display in general. But that's about all I know of the details. And this is also done in lines. So, and I guess as a final remark, these morphisms we've defined, Pn and P infinity, there's also a notion of duality for displays, and they are compatible with like duality, but I guess I'm out of time, so I probably should go into that. So I'll stop. Yeah.
I think I feel like it's quite not this one. I just
Or truncated.
okay, what is why?
Or truncated or
Yes.
Oh.
Just pretend.
oh using crystal engineering
Theory, yes, but
yeah. Yeah, I'm not sure if that's possible. I've only seen Lao's argument and that's reducing kind of in some sense the p-divisible groups. So yeah. I'm not sure.
Problem in part two.
What?
There'd be a problem in part two, like someone said earlier, that we want to define by P.
That I don't know, but I would guess that it's not a problem because you can still just like, we know enough about BTN that I feel like you could just write down a cover that has the BTN. But I'm not sure. Any other questions?